So in the first module, I mentioned that the next bull market is probably will be centered around zero knowledge proof. It's a very fascinating topic. I really, really love this topic. And there's a tremendous amount of content to be covered for zero knowledge proof. Initially, I was trying to make slides to cover the math and also a programming exercise. But it turns out that the math part takes a lot of time to prepare. So I can only get the math part work from end to end. And for the programming part, I will point you at certain libraries, and you can program on your own. In other words, this module, we will focus on going through one of the zero knowledge proof algorithm, the mathematics from end to end, explaining all the details and the concept behind them. I want you to keep in mind that because there's a lot of math in this module, it can feel pretty overwhelming at the beginning. And so as a personal story, I used to spend 1 year in neuroscience, brain cognitive science. And one thing I learned from that is everything in our thoughts, our cognition is underneath that is essentially a chemical secretion and a neural connection. What I'm trying to say is that your brain is like a muscle. You will exercise. When you exercise certain part, it will become stronger. If you have not worked with this kind of math frequently before, it might feel very hard to understand. And you might need to look at it several times a day for maybe 10 or 20 days. And maybe suddenly one day in the morning, you wake up, say, okay, I got it. I understand what does it mean. It's not exactly, you suddenly got it, but it's your neurons grow in your brain to support the cognition of this concept. So at the beginning, don't try to understand everything. Just follow slowly, one step at a time. And over time, you will find it easier to understand. It's not exactly, oh, I don't understand this. It's overwhelming. It's just like you have not trained this muscle for a long time. If you find it overwhelming. So we will first talk about the problem formulation, and there's a bunch of steps in the zero knowledge proof construction. And finally, there will be some brief, but that will be tomorrow. Talk about some programming environment, what you can do with zero knowledge proof, and the other ongoing research and development. I mentioned to you earlier that zero knowledge proof is a very actively developed area. It's not as mature as DeFi or ERC20. So the knowledge and concept tools in this area it's chaotic or mass. But it is a very fascinating thing. So here is the basic problem. Imagine in the Web2 world or in the setup, there is a server that let you submit queries, like Google, that you can query, you can search, or it's a Facebook, you can search for your network, or like Wikipedia, you can search for certain concept. Basically, it's a server that you send over a query, and it will return output to you. During this execution of this query, the server probably will use some information that it wants to keep private. Like it might have a ranking database for your friend. It might have this private structure to encode the internet. It might just have something it doesn't want the other to learn. Maybe it's like trading secret. It might have maybe like a patient private information. No matter what the reason, it just have some info it doesn't want to show you. So this is a type of competition we are pretty familiar with in Web2. We use Google, Facebook all the time. But there's a few questions we have not asked a lot so far. The user is mostly concerned about two questions. One is, how can I be sure the server returned the correct output? Like, how can I know? Maybe the server has a bug, or maybe the server tried to return something wrong. So how can I know? Like, that's the first question. The second question is, how can I verify quickly? I don't want to, go through a lot of resources. How can I verify this, the integrity of the result very efficiently? And on the server side, of course, the server want to prevent the information from being leaked. You want to keep the confidentiality of the private database. So there is this conflict of interest here between the user and the server. Specifically, in the zero knowledge proof setup, so that is a problem. In the zero knowledge proof setup, the server, besides executing the query, it will also generate a proof, some kind of information to convince the user that the execution of this computation is correct. And on the user side, there will be a verifier to verify that indeed this query indeed maps to the output, and by simply examining the proof. So this is a general proof, zero knowledge proof setup. I want to deviate a little bit to talk about why this is important and why is it significant. Because so far, as a computer scientist or as a programmer, we are dealing with programs and computation all the time. We write a program, it runs, we enter something, it outputs something. We don't really think about, like, did the program run correctly, right? The program can run incorrectly for many different reasons. Maybe there's some cosmic rays from the universe hit the electron and flip a bit, and the program miscalculated things. Or maybe the program has a bug. Or maybe some hacker entered the program, changed it. Or maybe when we talk to the remote server, the server might be maliciously changed the code, maybe to cheat or whatever. So there is this kind of trust. This gap of trust is always there. We always don't know if the program executed correctly. It's just that so far we didn't care that much. If you run the program 10 times, it gives you the same result. You feel like I'm confident, but maybe make the same mistake in 10 times. So far, I think in the whole computer science and the software industry, we have not looked at the correctness of execution that much. Only except in some area where the mistake can lead to disaster, like a airplane or like a rocket. In those areas, people look at the correctness of execution really, really seriously. But in most of the software, like Windows, Linux, or Google, people don't really think about that. We usually just like execute it. You get a result. It looks correct, then fine. We don't care the rest. But zero knowledge proof allow us to bridge up this gap of trust, to really know that the program actually executed correctly. And not only that, you can verify that in the instant. In other words, no matter how long the execution takes, no matter how complicated the execution is, maybe it has a billion step or 10 billion step, zero knowledge proof allow us to verify the correctness of all these billion steps in constant time. So that is an extremely powerful property, and it's quite intuitive. How can you verify a million things at the same time in constant time? So a lot of things, including me, a lot of people, including me, was very intrigued by this property at the beginning. Like, how can you do that? It's like one analogy I like to give people is like, for example, I give this person, for example, I wrote a book, and I want someone to help me edit the book. Say, if you see this grammar mistake, correct this way. Basically, it's a list of rules. I want to ask someone to help me correct the book. 3 months later, the person finished the job and handed me the corrected book. Now, how can I tell if the person has done it properly, has done it correctly? Maybe I can go through them one by one, go through all the page one by one and see if every page is correct. If I go through them, everything is good, I'm convinced. But zero knowledge proof has a better way. I can just verify all of the page in one instant. So that's so much for the intuition for zero knowledge proof. And next, I will directly go into the mathematics for the zero knowledge proof. Of course, what I just described, spent probably 5 minutes to talk about, is this question: how can I verify it efficiently? Verify all this step in one instant. But also there is also the confidentiality quality as well. So this is the whole setup of the zero knowledge proof. It looks really complicated, but there is only really 3 important concepts. So I'll go through them one by one. So on the top left is the problem, right? We have a program, we have private input, we have public input, and we have public output. The problem is to verify that given the private input and the public input, the program indeed give the public output. That's the proof we want. That's the thing we want to prove, and also we want to verify. And also in this verification, we don't have access to the private input. We only know the program, the public input, and the public output. So that is, I want to look at the upper left to see that is the problem. You can ignore all this structure for now because this is not supposed to be understood at this point, but we will walk, it's just like a map, walk over them one by one to eventually understand how it works. There are several key ideas on how to prove this property in an instant. The first is we can transform the program or execution or computation, no matter what you call it, into polynomials. Usually we write programs line by line, but we can apply a bunch of mathematical transformation to transform a program into a set of polynomials. So that is the first key concept in zero knowledge proof. The second concept is that we want to test. The first concept is not only translate into polynomial, but also translate the problem of verifying execution correctness into testing if the polynomial has certain property. For example, we want to test if the polynomial is 0 everywhere. We want to test the one polynomial if it's 0, basically. So that's the first step, translating verification problem into a polynomial testing problem. The second step is that there is this property of in algebra that you can test whether a polynomial is 0 everywhere by only looking at one of its points. The intuition is like this. I'll go into that in a moment. For a polynomial with a limited degree, for example, the third degree, like because the polynomial has many terms, like x to the power of 1000, then it's a 1000 degree polynomial. For any polynomial with limited degree, it only intersects with the x exercise at limited finite number of points. If it's a quadratic polynomial, then it interacts with the x exercise at 2 points. So if you randomly sample one point x, the chance that it will intersect with those points at 0 is the probability is 0. In other words, if you sample one of the point, if you randomly sample a point and find that that point is evaluated to 0 as a point, then the probability of the whole polynomial being 0 everywhere is 1. So it might be a little confusing at this point, but at some point slides it will become clear. Basically, the first step is translating the verification problem into polynomial verification, a polynomial testing problem. The second step saying that we can quickly solve the polynomial testing problem. And the third step, which is elliptic curve in cryptography on the bottom right, I think that is probably the most complicated thing in this specific zero knowledge proof setup. and I will go through that as well. So that is that's a very key component in this zero knowledge proof setup. So I also want to mention that there are many different zero knowledge proof algorithms. What we're introduced here is called Growth 16 zero knowledge proof. Zero knowledge proof also called ZK snark. The 16 means this algorithm was introduced in 2016, 8 years ago. The proof algorithm nowadays is more advanced and more efficient, but this one, just like Uniswap v2, it's classic and still relatively simple compared to the new one. And it has all the amazing opportunity already encoded here. Pretty much, I think this algorithm pretty much started the zero knowledge proof trend in blockchain. Again, you don't need to understand this whole thing. It's a map. We will explore this map part by part. So the first module we'll go through is how do you transform a program into a polynomials, and how do you transform the correctness verification problem into a polynomial testing problem. That's this whole section is about, and it concerns this a few blobs. By the way, there's a little legend here showing that that's the program, and some of the yellow things is proof. Is proof, and the black thing is a secret, etc. So let's start with a very simple program. This program takes an integer as input, and it raised to the third power, and then add all this thing up. If the input is 3, then you can easily calculate that the output is 35. So the first thing we want to translate this program into a circuit. We'll see quickly what does that mean. So on the right side, you can see that we essentially compile the left side program to the right side. We created 2 intermediate variables, sim1 and sim2. The sim1 is in times in, and y is sim1 times in. And sim2 is in times y, and output is sim2 plus 5. So why do we do this transformation? It's for simplicity. You see, on the right side, every line of statement only have 3 variables. 1 on the left and 2 on the right. On the right is either multiplication or addition. So this corresponding to some kind of circuits where you have multiplication gate or addition gate. So you can connect, you can draw a circuit to represent the right side. It's a graph. The first gate will be a multiplication gate. Both of the input will be the in number, and output will be sim1. It's essentially the exactly same computation, just written in a different form. There's nothing fundamentally changed here. And if in is 3, we can evaluate that sim1 is 9, y is sim1 times in is 27, sim2 is in plus y, which is 30, and output is sim2 plus 5 is 35. The next thing is, again, another a transformation of things. We arrange all these values into a vector S, the state vector. It's sometimes also called witness. Witness is a pretty weird name. It just means it sees all the state happening during the execution. When you execute a program, there's a lot of intermediate state, input, output. All of them is put in one vector. It has everything about all the states of the program execution. Here, we also put a 1 at the beginning. You will see why that is the case in a moment, and why a 1 in the beginning, and then everything else. We have 5 symbols in this execution, in sim1, y, sim2, and out. if in is 3, this state variable will be, this state vector will be 1, 3, 35, 9, 27, and 30. The order of this vector doesn't matter, but by convention, usually we put 1 at the beginning, then the input, then the output, then all the intermediate variables. But that doesn't affect the math at all. So now we can rewrite, again, this is a transformation of things. We just rewrite the same logic into a different form. I think after a few slides, you will see that I think this is common in math. You just transform the representation of the same thing represented this way and that way, gradually transform into the form you want, such that you can do things on the end form. So first we look at this operator called inner product. You can compute the inner product of two vectors by multiplying them element-wise and then sum them together. So that if you compute the inner product of S and this vector, sorry, I think I cannot show you the pointer here. So if you compute the inner product of S and this vector, you end up getting in, because this one, it multiplied in and you get in, everything else multiplied to 0. And if you compute the inner product between S and this vector, you get sim1. And then you can rewrite this statement, this specific statement. Remember, the program was rewritten into a list of statements. For each of these statements, you can rewrite it in the form of 3 inner products. Just put the state vector here, a witness here, and use this vector to take one element out. And here, in the inner product, to take another element. And here is also the third element. So you can rewrite, you can transform the instruction into this inner product form. And you could do that for all the, 4 different lines. You get an equation for each line. Note that this thing, the inner product, it can have two values. So given S in that form, this one gives you sim2 plus 5. And here it will just be 1. You can see that the 1 at the beginning of S allow us to represent a constant, not only variables in this. The sim2 plus 5 times 1. And I think here is the same. It's a in plus y times 1. So when I first look at all of this, I think the biggest question I have is why? Like, why do you want to do all of this transformation? I will explain this more clearly later, but I think the short answer is that I think in mathematics, everything it's like a graph. You have a lot of entities, like numbers, polynomials, programs. Those are entities, and the very key thing in mathematics are different theorems, like theoretical results. The theorems are acting like edges. Like if you do this, it's equal to that. If you multiply this one, you can get that. So sometimes you can think about the mathematics is like a graph. Like all the vertices are different concepts, and the theorems will connect them together. So for zero knowledge proof, you can think about like the problem we start with is at here, and the conclusion we want to know, verifying its correctness, is on different place. Now, how can we go from here to there? It's essentially a path-finding problem. You want to see how can I go from this program public input, public output to this, verifying correctness destination. And this is essentially the path people have found. They find that if we go to polynomial first, then we go to this, quick polynomial testing, and then go to elliptic curve in cryptography, you can actually go from the start point to the destination. Why we don't translate program into a different form, possibly simpler form, is because we have not found a way to go from the start point through that simpler form to the destination. So I think that's an intuitive explanation on why we're doing all this, complicated things. It's just because polynomial has some properties that program does not have. So by transforming the program into polynomials, we can do things that are more powerful than we can do on the program. So this specific form is called rank 1 constraint system. Rank 1 essentially means like each computation is one step or one gate. And just like, and there's another dichotomy I want to highlight here, which is the right side is not only a list of statements, it's not only a list of instructions for you to execute, but the right side also defines what does correctness of the program means. In other words, the right side, you can think about you can look at it from two different angles. The first angle is assignment statement. You compute the right side, assign to the left. Compute right, assign to the left. So that's like the execution point of view. The second angle you can understand the right side is that those are all equations. They are constraints, meaning that if sim1 equals to that, y equals to that, in other words, people give you number for sim1 and y and in, and you check those numbers against those equations. If all those equations holds, if all those equations are true, then you can say that this number, this set of number is from a correct execution of the program. Let me repeat. I think this is a very important thing. So this is not only an execution instruction of the program, but it also defines what does it mean by correct execution. For example, someone might tell you, say, hey, I execute the program and I got this numbers for this state. And now, in practice, there could be like a billion numbers. There could be a lot of numbers in the states. Now the question for you is, how can I tell if this list of vectors is from a correct execution of the program, or maybe it just randomly generate, garbage? What you do is you put all those numbers into the equation on the right, and if all the equations are true, then you are convinced that these numbers are actually from a correct execution of the program. I'll let that sink in a little bit. Because that 4 lines of equation is a definition of the program's correctness. By translating into this R1CS, the R1CS here, we can see the R1CS here defines the correctness of the program. And we can rearrange all those things into this matrix form. It's still the same thing. Let me see. Yeah. So this matrix basically means that there are 4 columns corresponding to the 4th step in the program, and there are 6 rows corresponding to the 6 states in the state vector. And this operator, it's called a Hadamard product. It's pretty simple, just the element-wise multiplication. And because S is this vector, you do matrix multiplication, you will get exactly these four equations. So basically, we translate the program firstly into this simpler form, which is also a definition of correctness. Then we translate into these equations by using inner product with the state variables, state vector. And then we rearrange them into the matrix form. So all of this is exactly the same thing, just representing different ways. Yeah, like we mentioned earlier, now someone can ask us, I have this vector and we need to answer, is this vector a correct execution program? You can simply put S into this equation. And if the equation holds, like here, then we essentially prove that it's a correct execution. If this equation doesn't hold, then we disprove its correctness. Of course, so far this check is slow. We need to do like a matrix multiplication. We need to, if the execution has a billion step, we need to check a billion entries. So it's very slow, but it does define the correctness of the program. And next is a further transformation of the problem. Transform the R1CS into something called quadratic arithmetic program. So let's look at this matrix on the left that we just looked at just now. Again, I would imagine if this is your first time look at this, it will be overwhelming. Please just relax. It will not be in the quiz. Just relax and look at this. Let it, soak in. And over time, I think you will get a feel of what all this is about. Just look at the first row as this matrix, 0, 0, 0, 5. We can do something called Lagrange interpolation to find the polynomial that evaluates to exactly 0, 0, 0, 5 at x equals to 1, 2, 3, 4 on the right, like this. And let's call this one A1x. Because we have four columns corresponding to 4 steps of the program, you can think about these 4 points as corresponding to the 4 different steps to the program. And the 6 rows are 6 states. Therefore, the first row, this polynomial is characterizing the first state. And this is a pretty fundamental step. By fundamental, I mean that we are not working with the same thing anymore. Like all the previous steps, we are essentially transforming the same thing from the one representation to the other. But here, something different, because this polynomial does not only have value at x equal to 1, 2, 3, 4. It also has value on other x, like -1, like 100. And those values might not make any sense. What does it mean if we only have 4 steps? So in a few steps, we will see why this is very important. Like in the Uniswap v2 code, we essentially concentrate to a few lines of important code, like everything else was, surrounding those a few important lines of code. I would say this is an important step in zero-knowledge proof. The previous step essentially, rearrange things, change things the same way, but this step fundamentally changed something. And then we can, do the same thing for all the 6 rows, and we come up with different polynomials, 6 different polynomials. You can check that they match all the numbers here, and all of them have value at x equal to 1, 2, 3, 4. But they also have values in other x as well. And we arrange them into this form. We just say this is the vector of all these polynomials corresponding to the different states for the A matrix. A matrix is not the entire computation. It's just like a 1/3 of computation. I'm not sure if you see these 3 matrices. We temporarily call them ABC. So A matrix is just 1/3 of this whole thing, and we can do this interpolation. So this one is so this slide, what we are looking at is at the end of the day is essentially a different way of computing this. A different way of computing this. Here we are using S times the matrix to compute this value. And here we can use the polynomial to compute exactly the same thing. Let me explain how this works. Because we have 6 rows, each one corresponding to a polynomial, we have 6 entries in the witness vector. We just like line them here and multiply them element-wise. After multiplication, we add all this polynomial into a single one. So this polynomial, we call it AX, is essentially a weighted sum of all these 6 different polynomials. And the weights are the values in this witness vector, state vector. And if you check, it's also an inner product. The S is a vector, and the polynomials is also we put it into vector. So by compute the inner product between the witness and the polynomial vector, we end up getting this whole this vector. And this vector will be different for different execution vector, different witness vectors. So if you execute the program twice with different input, you will end up with different witness vector, and you will end up with different polynomial here. If you plot this one out, you will see that it evaluates to 3, 9, 30, and 35 at x equal to 1, 2, 3, 4. If you look at earlier, you will see that that's exactly the 4 numbers we get by compute the inner product between S and this matrix. So this confirms that this is essentially a different way to compute the same thing, just use polynomials. So far we have not seen why polynomial make a difference, but we just want to show you that by transforming it into polynomial, we can compute exactly the same number. Therefore, we can write the program correctness checking criteria using polynomials. Remember that this equation, if this equation checks to true, then the program executed correctly. So we can state the same, we can write the same statement using polynomials because we can compute these 4 numbers. So this slide will explain why polynomial is different than the. So here basically we just the Lagrange interpolation jump us from this representation into this. But why? Why is this better? They compute the same thing, but the power from the right, why the right side is more powerful because it has values on other points. It has values on the entire real number field. So it's not only limited to x equal to 1, 2, 3, 4. And the zero knowledge proof needs the entire axis, not just x equal to 1, 2, 3, 4. So by expanding the problem to the whole axis, we will later be able to use some other powerful mathematical tool to check this. So this is essentially explaining why we want to go all the way to here. And we can do the exactly same thing for B and C. Same thing, 6 polynomials because we have 6 states, 4 points on the axis because we have 4 execution steps. And we can do the same thing, inner product between the state vector, witness vector, and the polynomial vector to compute the weighted sum. And the equation still holds. Yeah, so you can essentially, like this two, the Hadamard product between these two equals to that one is the criteria of the correct execution written in polynomial form. By rearrange this, ax times bx equal to cx at one point at x equal to 1, 2, 3, 4. That's a different way to write this equation. If you rearrange this one a little bit, you will reach this equation. Basically, ax times bx minus cx is 0 for x equal to 1, 2, 3, 4. As you can see at the bottom here. Let me just recap a little bit. You execute the program, you end up with a witness vector. You use the witness vector to compute the weighted sum of ax, bx, and cx. After that, you will get a single polynomial by computing ax times bx minus cx. And then you plot this polynomial out. If you find that this polynomial is 0 at all of the execution step points, then the execution is correct. You verify, you proved that this execution is correct because it's 0 at all this execution step. You don't really care what's the value here. You don't care about the value there. You also don't care about the value in the middle. As long as it's 0 on this integer points, you know the execution is correct because it can backtrack step by step to the initial definition of the execution. Okay, so we just did this recap. It's the same problem. We transform it step by step. So far, we have not directly used the power of the QAP yet. Okay, so the first module, let's summarize a little bit. We just transform the programming verification problem into a QAP problem. And we show that it's the identical problem. The next, we are just gonna show how can we check this. How can we check this one efficiently? So at this point, we want to prove this. Maybe not only 1, 2, 3, 4. If the program has n step, it will be 1, 2, 3 until n. It will concern this two box and also that mathematical lemma. There's an algebraic theorem saying that if this polynomial is 0 at x equal to 1, 2, 3, 4, then this polynomial can be divided, perfectly divided by this polynomial on the right side. Because on the right side, this polynomial evaluates to 0 at 1, 2, 3, 4. This is a different way to write it. You can basically, the left side polynomial is a multiplication of this polynomial with some other polynomials. For example, the polynomial we have seen previously, like this one, like basically this we have an example here, and that polynomial, if you compute it, you will find that it will be the multiplication of these two different polynomials. And this, by multiplying zx with hx, we get two more roots on this blue point because we have like a higher two degrees higher by multiplying zx with hx. In the zero-knowledge proof architecture, there's something called program preprocessor. It will translate the program into QAP. It's a first section, and then the program is executed. It will get a witness vector, and then the prover will use the witness vector to assemble A, B, C, and also find the H polynomial. And then the verifier, after look at this, you need to quickly verify whether A times B minus C is equal to Z times H. In other words, the verifier need to quickly check if this is true. If the verifier can quickly verify that equation, it means that it means that A times B minus C, this equation is 0 at all these integer points, because if A times B minus C can be represented as the Z times H, then according to this slide, and according to this algebraic theorem, this equation is 0 at the integer point. Any questions? Let me take a look. And this x can be simply obtained through polynomial division, A times B minus x divided by zx. That's a pretty typical algebraic operation, just polynomial division. Now the problem is, how can we check this equation quickly? The prover needs to do all the work to come up with A, B, C, and ZH. The verifier needs to verify that. In the zero-knowledge proof world, we don't really care that much if the prover is slow, but we really care if the verification is quick. There's some practical reason for that, but it's also the property we want to optimize. Because, for example, one of the application of zero-knowledge proof is it's a blockchain verification. Right now, all the Ethereum node will replay all the transactions from the beginning of the chain or not, maybe not all the transactions. You will play all the transactions in each block, or when it verifies the block. The hope here of applying zero-knowledge proof to Ethereum or to blockchain is that you can take a lot of time to produce the block or to produce the proof of the execution of the block, but you want everyone to verify the block very quickly. That's one of the reasons why we want to optimize for verification speed and care not as much about whether proof is quick. Again, the terminology here is this is the prover, this is the verifier. The prover generates all these polynomials. The verifier needs to verify them quickly. But how could the verifier verify quickly, given that these polynomials are extremely huge? It could be billions of items, elements. So this lemma is a key step because there are infinite number of points on the x-axis. Given a polynomial with finite degrees, like px, like that one is degree 6, it will intersect with x-axis at finite number of points. A degree 6 polynomial will interact with x-axis at most 6 points. So if you randomly pick x, px is 0 with probability 0. It's very unlikely that you will hit one of these points exactly, because there are infinite number of points on the x-axis. If you randomly pick one, the chance you will hit any of these points is 0. Therefore, if you actually hit a point that is 0, it's very likely this polynomial is 0 everywhere. I think there's like a Bayesian or probability calculation here, because it's very unlikely this happens. So if you pick a point and if it's evaluated to 0, then x is 0 everywhere with probability 1. So far, any questions here? Yeah, this is a very fundamental. This is a very important step. Therefore, checking the equality here can be done by picking a random point on the x-axis and see if this equation holds at that single point. if this equation is true at that single point, we can conclude with confidence or with probability 1 that this equation is true everywhere. So this is a very, of course, this is a very powerful theorem, and it completely transformed the problem. We are no longer try to check if all these points are 0. You know, we are no longer checking if this polynomial is 0 at 1, 2, 3, 4. We just want to check if if this polynomial if this polynomial equation holds at a randomly picked point. So this step has a fundamental change of the nature of the problem. The verifier only need to verify that at a single point. So there are some remaining problem here. One of them is evaluating a high degree polynomial at a single point, even it's a single point, it's still very slow, right? You need to, if it's a degree of billion, you need to compute all these different terms and find what the polynomial is at this specific point. And also, so far we have not addressed that the executor maybe don't want to leak information. This state vector might have information that are private to the executor. So I think we will stop at this point today and continue tomorrow. And yesterday we mostly talked about the first two steps in the zero knowledge proof. What we covered is the transformation of the zero knowledge proof problem, which is given a program and some input and output. You want to prove that the program actually produced that output given the input. There is also this privacy concern, but we have not talked about that yet. The first, the problem is basically prove the program indeed provide this output given the input. And it's a big algorithm design. And so the first step is to convert the program through many steps, eventually into polynomial testing problem. Let me find the slide. Basically, transform the problem of verifying program as execution correctness into the problem of testing this polynomial is 0 on this 4 different points, or if your program take n step, it will be n on all this 0 on all these n points, and that can be further transformed into testing this polynomial. Because if the polynomial on the left side is 0 at this discrete points, then it must be divisible by this polynomial, and therefore it can be written in this form. So in the prover verifier setup, the prover it's the prover's burden to provide this hx polynomial to show to the verifier that, hey, this polynomial indeed can be divisible by this z polynomial, and the verifier just need to verify that the left side of this equation and the right side of the equation are identical. And this problem of verifying these two polynomials are identical is called a polynomial testing problem, and can be further simplified through the Schwarz-Zippel lemma into the problem of testing only on one point. You randomly pick a point. If on this point these two polynomials are evaluated to the same value, then you can be confident that these two polynomials are identical everywhere with probability 1. And we talk about this methodology of, like, a lot of these steps are essentially transforming problem through different transformations, but there are 2 steps that have some fundamental change. One is Lagrange interpolation from a discrete representation into a representation that span the whole axis, And the other fundamental transformation is the application of the lemma, so that it's transforming from testing two polynomial testing if they're identical into the problem of testing these two polynomials on a single point. There are a few points. So if we think about from a zero knowledge proof point of view, there are some problem remains. It's not like we can just easily test the two top polynomial on a single point. There are some points. I list the problem here. The first problem is that evaluating the high degree polynomial at a single point is still slow. If the polynomial has n degree, then the time to evaluate is at least O(n). It's a linear complexity. But the other problem is, so far we have not addressed the confidentiality problem. Basically, this vector was used to assemble those polynomials. Therefore, if you send the polynomials to the verifier for verification, the verifier is not only slow for the verifier to verify them, but also the verifier can reverse engineer these weights to figure out some privacy, some secrets the prover do not want to share with the verifier. So these two problems, we need to solve them in order to satisfy the requirement for the zero knowledge proof. And today we will introduce this methodology that achieve both of this property. Before I start introducing this, do keep in mind that there's more than one way to achieve this goal, and the elliptic curve cryptography is one of them. It was, I think, was the first mature, first proposal in 2016 to solve the problem. But later there are other ways to solve exactly these two problems. So elliptic curve cryptography, I'm not sure. So how many of you have worked with elliptic curve before? Okay, so I will guess like so most people have not worked with elliptic curve before. So let me introduce them step by step. Yeah, well, first we'll introduce a bunch of things related to elliptic curve. So elliptic curve can sound like a very scary thing, but indeed is very simple. Its representation is just middle school algebra. Just this, here's an equation in this form, and any points. Of course, we need to in practice we will specify what a and b is, while y and x are variables. Elliptic curve is basically all the points on the plane that satisfy this equation. It can look like this, but it can also look like any of this by tweaking the a and b into using different values of a and b. You can think it's just like a 1 degree higher than parabolic curves. We have linear, it's the first degree, and the parabolic, second degree, and then third degree is elliptic curve. So elliptic curve does bring some very interesting properties that are not does not exist on lower degree polynomial. One of the things is we can define this operation of addition on the points on elliptic curve. For example, here are 2 points P and Q. You can draw a line connecting P and Q, and this line usually intersect with another point on the elliptic curve, which is R. And you can see that the elliptic curve is symmetric to fall across the x-axis. If you take the mirror of that point, you get the addition of these 2 points. So this is just addition. This is just definition of the addition on elliptic curve. There is only one line that does not intersect with the third point, which is if you take this leftmost point here, and if you draw a tangential line of that, then it does not intersect with anything else. But that's a special point. We can ignore that for now. If you pick any other points, for example, these 2 points, and it's going to intersect somewhere down here. So we do not need to understand the math of elliptic curve deeply. We just need to know that give any points on elliptic curve, you can calculate their addition. And you calculate that by draw a line. It will intersect with the curve on a third point, take the mirror of that point, and then you get addition of the 2 points. There is a closed form to compute this. You do not need to always compute it geometrically by drawing a line. So that's addition. And I will immediately introduce the concept of prime fields. The whole point of prime fields is that if you look at this curve is defined on the real numbers. And real number, it does not exist in computer. In computer, we only have float points numbers, and there's a lot of problem for float point number for elliptic curve. One is that float point have rounding off errors. It's non-deterministic, and it's also slower to compute than integers. And there's also another problem, which is that float point is not as secure as discrete point, because you take the log, take logs on float point number is pretty easy. But if you take a log modular math, if you take log with modular arithmetic on integers, it's a very, very hard problem. And the hardness of this problem contribute to the security of elliptic curve. It will become more clear in a moment once I introduce the previous slides. The prime field is the integer, is the number we use to define elliptic curve and using zero knowledge proof. It's not. It's a pretty simple concept. Basically, give a prime number. Just name any prime number. It can be large or small, and the prime field is basically the collection of all the integers up to p minus 1, from 0 to p minus 1. And on this prime fields, we can define addition, subtraction, or multiplication exactly the same way. Only the difference is that you are modular p at the end. For example, 4 plus 6, modular 7 will be 3. 4 minus 6, which is minus 2, modular 7 will be 5. 4 times 6, 24, modular 7 is 3. And the division is defined slightly more complicated because you cannot directly compute it easily. X divided by y equals to z, such that x times y. No, so there's a typo here. This should be, I think, this should be z. Z times y mod p is x. Basically, it's a reverse of the multiplication. And you can test that 4 divided by 6 equal modulo 7 is 3, because 3 times 6 is 18, which modulo 7 is 4. So on this prime field, everything works exactly the same as normal arithmetics. The only difference is that it's all integers and everything is modular p, and p is a prime number. So this is more like an implementation level detail, but it is very important implementation. But math-wise, it does not change anything about elliptic curve. So this will look like this will be how elliptic curve looks like over prime field. It doesn't look like exactly like a curve, but it's the same thing as the curve in the sense that it's all the points on this field that satisfy this equation. So here the prime number is 23. So p is 23 here. Therefore, the integers goes from 0 to 22 on both axes. And all the points on this field that satisfy this equation is here. And you can see that it's still symmetric across vertically. And you can still define addition exactly the same way. Pick 2 points, you can draw a line, and this line must intersect with another point, and mirror that point, you get their addition. A plus B will equal to C. Everything works exactly the same. Because we have quite a lot of entities in this proof, we will use this lowercase letter to define the scalars. Basically, it's a number. And in the prime field implementation, there will be prime field number, integer. I use AX, AIX, this kind of notation to represent polynomials. And finally, we use this uppercase letter to represent the points on the curve. Once we define elliptic curve, no matter it's on a real number or prime fields, and we also define their addition, we can start to define their scalar multiplication. So far, we're still building this basic concept about elliptic curve. And once we build the concept enough, you will see why they can fit into the zero knowledge proof. So P as a number, as a point on the curve, P times 2 is P plus P, which is you take the P and draw a tangential line across on that point, and it will intersect with another point on the curve. And you mirror that, you will get P plus P equals to 2P. And you can do this thing the same way, P plus P. If you add P K times together, you get P time multiplied by K. I think, yeah, this is the intuition is the same as any kind of arithmetics. You add one number K times, becomes P times K. So the definition of addition leads to the definition of a scalar multiplication. This P and K are, the P is a point on the curve, and the K is a number. So they are not exactly the same thing. And this is a theorem in elliptic curve that if you give 2 points, one is called G, the other one Q, which is a G times a scalar number. So if you give G and Q, if you release G and Q as public points and you keep K as a secret, the theorem says that it's extremely difficult to find K from G and Q. So this is, and I think at this point, this deviates from the traditional math, because in traditional math, if you have two numbers multiplied together, get a third number, then if you publish the third number and one of the two numbers you use, it's very easy to find the third number, the other number. In other words, division is very easy in ordinary numbers, real number. But division here is extremely hard. You cannot, there's no, we don't know any algorithm that you can recover the K efficiently from G and Q. The only way you can do that is to try all the possible Ks. And this is the reason behind the security of elliptic cryptography. This also means that G times K can be used as a hash function for K. We can hash K into something else that is very hard to reverse guess K. It's a one-way function, a trapdoor function. Okay, I'll finish this slide, then we can stop for a few seconds for questions if there are any. If you have 2 points, they are the same points G multiplied by different scalars, then you can perform addition on these 2 points to get. So homomorphism is a word that basically means that you can do computation on the encrypted form, or you can do computation on the hashed data. For example, I want to compute K1 plus K2, but I do not know these two numbers. I only know the Q1 and Q2, which is the G times K1 and G times K2. In other words, I only know these two numbers hash. I don't know these two numbers. And the additive homomorphism means that we were able to compute this, do this computation on their encrypted form, on their hashed form. Here, Q1 plus Q2 is equal to G times K1 plus G times K2. And that's exactly the same thing as G times K1 plus K2. This means that you can, yeah, again, let me repeat it. You can do computation on numbers that are kept as secret. You don't know the number. You only know their encrypted hashed form. You can do the computation that way just by using their encrypted form. So that's about like half of the definition related to elliptic curve. Any questions? I'll pause a little bit. Any questions? Is everyone preparing for the quiz, right? No, no. They use a hash function. They use a different way to do this. Basically, so this, let me go back a little bit. So there are different ways to solve this problem, and the solution basically means that you can. So these are all kind of called polynomial commitment. Yeah, polynomial commitment means that you can. It's like a hash for polynomial. You have one polynomial here that you want to keep secret, or it's too big, so you compute a hash for this polynomial, and which is small, right? And you publish this hash. And using this hash, people can evaluate property about the polynomial at certain points. You know what? Do you know what? So you know what I'm trying to say is that here there's a huge polynomial here, and everyone can evaluate this polynomial at certain points. But now that's too slow and also leak secret. So polynomial commitment lets you create a very condensed summarization of this polynomial, which is not only like does not leak information, but it also allows you to quickly evaluate this polynomial at a certain point. And Stark is one way to do that, and this elliptic curve is another way to do that. And there's also a third way, I think, called IPA to do that. There's quite many different ways to do that. Different way of hashing polynomials. IPA is another way. As an inner product argument, I think that's the three major ones. There are definitely more. There are probably, I think, later I have one slide to show that once everything has been talked about. I think I have one slide to talk about that. Maybe this one. But that will be later, I think. Okay, thanks. Is it better? Okay, I feel like maybe we should like have the quiz first. I feel like now no one has the. My bad. We should have quiz first because I really want you to enjoy this because this is a really nice stuff and it will benefit you if you work in blockchain in the next few years. Also, don't stress too much about the quiz. I think. I mean, this is not a promise, but I don't think anyone will fail this class. So don't stress too much about this. And yeah, don't stress. Yeah, I think the quiz is not only to test your understanding, but it also the quiz itself is part of the learning. Like you might see, oh, this problem, I don't know how it works. Maybe you know. Any question? Okay. Yeah. Okay. Let's keep going, because I think if you find something that's confusing, it's better to let me know immediately, because later stuff build on this. If this is confusing, it will only get more confusing over time. Because I also want to know which part I can explain more clearly. I think elliptic curve is not something I'm like a super expert in. So some of this I feel like I cannot explain the why behind them very well. For example, why do you define the addition this way? Like this is not a question I can answer. I can only tell what it does, and if you do this way, then you get this nice property. Okay, let me keep going to the next part, and later you can also watch the video. So pairing is like I think pairing is the hardest part in zero knowledge proof. It is to solve a gap in the previous definition of elliptic curve. Previous definition of elliptic curve, we define the curve, we define points on the curve, we define addition, and using addition to define scalar multiplication. And on top of scalar multiplication, we show that this definition, the previous definition of addition and scalar multiplication, gives you additive homomorphism. There is also this important property that scalar multiplication is a one-way function. One-way function means it's super easy to compute one way, but it's super hard to compute the other way. It's also called trapdoor function. Is once you go from one direction to the other direction, you are trapped there. You cannot go back. And this is a lot of this trapdoor function in cryptography make them secure. Because if you can easily go back, you can easily decrypt the message. So this is everything we have so far. But there's a very key ingredient missing here, which is we cannot multiply 2 points on elliptic curve. So far, we can add 2 points together. We can multiply a point with a number, but we have no multiplication of number. What does it mean? This is not well defined. There's no definition of the points multiplication. And it turns out that multiplication is needed in checking zero knowledge proof. And that's why pairing, this concept come in. The pairing is defined in a very generic way. In other words, pairing was not defined as this specific way of compute things. Pairing basically means like anything that has this property called bilinearity. So bilinearity is these two equations. So a bilinear operator is an operator that takes 2 arguments and produce 1 value. It's written as E and take two arguments. A pairing operator is bilinear in the sense that if you have this operation, it can be written as this, and if you have this operation, you can written as that. Anything satisfy these 2 property can be called a bilinear operator, and pairing is essentially a bilinear operator. I think that's probably the same thing. I'm not sure, maybe there are other operator that's bilinear but not pairing, but in the world of zero knowledge proof, I think they are the same thing. And you can further check that if you have this so this pairing take 2 arguments. If one of them is a scalar multiplication between a point and a number, you can move this number to the other to the other points, and you can use the so yeah, we can derive a little bit. You can expand the first multiplication into this, then using the bilinearity you can expand that out. Then all of them can be shrinked into this form. And we do know that there are quite a few algorithms that is satisfying this bilinearity property and can be used in practice. In other words, if today you want to implement zero knowledge proof, you have a few algorithms to choose from to use as the pairing operator here. But specifically which one we choose or how they work, we don't need to understand them. We just need to know that there exists operator called pairing that satisfy this property. That's all we need to know. Okay, so this is an application of the pairing operator. Let's see what the pairing allows us to do. So given a Q, given two pairs of points, the first one is Q equals to P times A. The second pair of points is S equal to R times B. And the Q, P, R, S are both public points, and the A and B are secrets. We don't know about these two numbers. So now the question is, can we tell if A is equal to B? You know, this is not possible previously, right? Because Q and P, they are two different points, and S and R, they are two different points. If P and R are the same, then it's easy to tell because if P and R are the same, then A and B, and if A and B are equal to each other, then Q and S must be equal. But now Q, P, and R are different points, and pairing allows us to do that. Here is a simple derivation. You compute the pairing between Q and R, basically this point from the first pair and this point from the second pair. And Q is P times A. You can move A out and then put A into R. So now this becomes E, the pairing between E and P, between P and R times A. On the other hand, you can also compute, so EPS, we can compute the pairing between P and S, because S is R times B. So now you have two pairing, so now you have two values computed from pairing. One is between P and R times A. The other one is between P and R times B. Of course, if A equals to B, then this two pairing will be the same value. If A does not equal to B, then these two will not be the same value. So this is a pretty straightforward application of pairing, and specifically its bilinearity property. It allows us to do this very cool comparison between two secrets that was not possible without pairing. Okay, so next we will talk about a very critical step in zero knowledge proof, and everything we have built so far, I think it contribute, everything we have talked about so far in the elliptic curve contribute to this important property. It's called knowledge of exponent assumption. Yeah. So it goes like this. I think we need to slow down a little bit here. To give a pair of EC points P and Q, and the Q is P times a secret K. P, Q, and public K is a secret. And now, if someone else present a pair of points R and S, such that S is equal to R times K. In other words, we have a pair of points. One of them is the other multiplied by K. K is a secret. So now, if someone else present us a pair of points, and these 2 points is also one point is the other point times by K. The K is the same as our secret, and we can check that using pairing, right? We just talk about it. We can check this if we can check if their points is also differ by a scalar K. If we find that this other pair points is also differed by k, then this assumption basically concludes that R must be derived from P. For example, R must be a linear combination of K. R may be the P times something. Let me explain a little bit what does this mean. R must be derived from P. One way to derive R from P is to simply multiply P with another scalar, for example, A. So R is equal to P times A. So if R is equal to P times A, then we can say R is computed using P. It's derived from P. And then you can multiply Q with the same scalar to get S equal to Q times A. And you can follow this S equal to Q times A, and Q is P times K. Earlier, you remember that Q is one of the points we have earlier. P times K times A, then P times A, P times A is R, and it's R equals to K, R times K. So in other words, if we have a point, if we have a pair of points that differ, but that is one of the points is a multiplication of the other point by k. If someone else gives us a pair of points differ by the same number, then they must have used our point to come up with a pair. In other words, it's not possible for them to come up with a pair. It's not possible. It's very unlikely that they come up with a pair of points that differs exactly by our number. It's almost like they cannot decrypt our number. They must have used our pair of our pair of points, apply the same computation on both sides to get S and R. Does this make sense? Any question about this side? It just means like this connection between P and Q is very secret and very hard to figure out. So if you want to have another pair of points that has exactly the same secret connection, that's not possible. The only way to come up with another pair of points with the same secret connection is to take this pair of points and apply the same computation on them, like multiply P and Q both by 3, or like you do some other like a computation on both of them, and you can maintain this secret connection by k over that. And if you want to come up with a different pair, just guess. It's not possible because you cannot guess k from P and Q. Okay. Let's go to let's expand a little further. So here is a more advanced way of applying the knowledge of exponent. What? Do you have a question? Knowledge what? Sunkeness. Can you spell the next second word? No, like knowledge what? Soundness. Completeness as soundness. I think soundness means if you don't have valid computation, you cannot come up with yeah. That's a very good question. Let me try to understand what you say. Wait, let me try to answer. You mean if you don't have that, then you can. So I think I will say so. Let's pick this apart. So you mean the soundness of proof it means that if you do not have a Yeah. I think it's the same thing, but this is applied like almost universally everywhere. So yeah, let's talk about this in detail. So here, I think you can say that the person who come up with SNR, they have two ways to get SNR. One is they apply the same computation on P and Q to get SNR. Right. So first way they can do that is to like multiply P and Q both by 3, and they can get SNR. So that's one way to get SNR. You mean we can back infer how did they do that? The other possibility is they just randomly guess SNR, and it happens to be differ by k. Yeah, we just think like the second way is much less likely than the first way. Therefore, we conclude that 99.999%. Yeah, they must go the first way to it's not like they know k, but they use the p and q to compute SNR. Yeah, and I think it's almost but this same argument is used in many places, like in the Schwarz-Zeppel lemma. It's the same thing, right? If you randomly pick a point, it can also just happen to land on the point that is 0. It's just very unlikely. Yeah, like the hash is the same thing. Like if you know the hash, something hash to this thing, then you probably it's just like password. When I log into a website, I can also just randomly guess someone else's password. Okay. Cool. Yeah, great question. Any other question about all this slide? Okay, let's keep going. So here we'll just talk about two pair points, but you can also expand the same argument to multiple pair of points, like a Q1, QP, Q2, Q2, QP2. So all of these pair of points differ by k, and all of these points are public, and k is a secret. So we have this set up. So this is what with the context we have. And now someone else present a pair of points R and S. And we can also conclude that, let me see. We can also conclude, and we can also check that these 2 points differ by k. And then we can be sure that we can be sure that R will be computed from P1, P2, P3, and Pn. In other words, we have all these point pairs that have this secret link already established, and the secret is kept a secret. Now you present a new pair of points that have this secret link. This new pair of points must be computed using the previous list of points. For example, it will just be a linear combination of the previous point. Yeah, because here on elliptic curve, we can only do scalar multiplication and addition. So it just means that this point must be a linear combination of all these points. Because if you don't do that, you will randomly guess P and S and R. It's very hard that they happen to be differ by K. Does this make sense? It's the same thing like previous. So just previously, we only give you one pair of points with secret link you can use. But here, if you give many different points, you can assemble them. But as long as you do the same thing on the P side and the Q side, you will end up with the pair of points that differ by K. And the intuition here is that in some way, we can encode the program like this. We can encode the program into all these pair of points, and the proof will just be this pair of points. And by providing this to set up, if this proof is different by this secret key, and the program all differ by secret key, by looking at this information, we can conclude that this proof must be a linear combination of the program, which means that this proof is indeed an execution of the program. So this is I think this is a pretty subtle but very important point. We will explain exactly how this works, but the program is encoded as a many pair of points on the elliptic curve, and the proof will end up being a pair of points on the elliptic curve that has the differ by the same secret as the program. Therefore, so the program points will be released as a public, like everyone knows that beforehand, because we're talking about program that is public and fixed. Everyone knows the program. Now the prover needs to prove that my input and output pair, the output is actually produced by the public program given this input. So the prover needs to convince everyone that my execution, my witness vector, my state vector is actually produced by executing that program. And go back to yesterday, it means proving that that polynomial equation holds. And that polynomial equation can be eventually translated into this list of pair of points, such that the prover just need to give a single pair of points to convince everyone that this pair of points is derived, is from actual execution of the program. Does that make sense? How does everyone else think? Like this must be confusing, right? I mean, the first time I look at it, it's very confusing. I mean, if you find this confusing, it's very normal. If you find this not confusing, then you probably have worked this before. It is very confusing. So it take me a long time to figure out what does this mean. But later when you understand how it works, you can go back to here to see that this is like this is really where the intuition is. Like if you think about like how can you use a single thing to in constant time check, you know, all of this billion thing works. This is how, like, because you have a billion things, and given this knowledge of exponential assumption, then you can say this single thing must be a, you know, a accurate summarization of this billion things. Yeah, so it's an intuition behind V1 verification of ON items, and it's also why elliptic curve can be used to solve zero knowledge proof. Like we mentioned, there are multiple ways to solve zero knowledge proof. Elliptic curve is one of them. It can solve it because of exactly this. Okay, so so far we have finished the introduction of elliptic curve cryptography. And next we will talk about how to use this elliptic curve cryptography to verify the integrity of the program. So we introduced elliptic curve, and now we will use elliptic curve to prove the integrity of the execution. It's all of this part. Now you can see that because you can see this is like involve many different blocks on the map. It's really the step where everything come together, like tie the knot together, so it can look like a lot. Previously, we just, you know, the polynomial is all here, the elliptic curve is all here, and Schwarz-Leppo lemma is all there. But now it's everything coming together. We will talk about them again one by one. So, so one thing we want to introduce is something called trusted third party. You can think about them as let me introduce what does that mean in a moment. So trusted third party picks a point on the x-axis. They just pick up x, randomly pick x. So this is related to the Schwarz-Leppo lemma. You want to randomly pick a point, and if these two polynomials are identical at that point, you can think they are identical everywhere. So this is that randomly pick. So this third party randomly picks a point, and this point has to be kept as a secret. So the trusted just means that this number is indeed kept as a secret. Like you cannot leak the secret to other people. I will explain what does all this mean, because if you think about that, if the prover pick the point, that prover can intentionally pick a point where these two different polynomial intersect, right? So these two polynomial are different, but they intersect at finite number point. So if you let the prover pick the point, the prover can cheat by picking the point where the polynomial intersect. If you let the verifier pick the points, that also works because the verifier needs to send the points to the prover, but then the prover will needs to evaluate the polynomial at that point, which is slow, but also prover can cheat because prover, might just say, oh, hey, they are identical, but the verifier has no way to know if the two polynomials are actually identical. Long story short, the setup in zero knowledge proof is that we pick a third party, a third trusted party, will pick the point, and this point is kept a secret. The prover doesn't know that. The verifier doesn't know that. And in a moment, we'll see why that's the case. If you think about, oh, why do we do this? I understand it can be confusing why we do this, but let's just assume that's the case. There's a third party who picked the number on the x-axis and keep that secret. We trust that this party actually kept a secret, does not tell the prover about it, does not tell the verifier about it. Then we evaluate all those polynomials. This polynomial was previously transformed from the whole program. So you remember, these polynomials are Lagrange interpolation of the programs. So we evaluate all these polynomials at this secret point k, and we get all these different evaluations. So if you are sensitive to all of this, you will see that we are gradually going toward the direction to evaluate. We are gradually going toward the direction, try to find a way to evaluate this. We're just trying to find some way to evaluate this equation in a way that is both fast and privacy preserving. So we are constructing a way to do that. We're go toward that direction step by step, slowly. We pick a secret point and you evaluate all these polynomials at that point. And so far, all of these are secret because if you know, like for example, A1, if you know the A1 at t, you probably can guess what t is. So all of these are secret. The trusted third party also pick a point on the elliptic curve, any point. Well, you can think about just any point. We just pick a point and we call it G. G means generator. Generator simply means that you can multiply G with another number scalar to reach other points on elliptic curve. And G is public. So remember, like previously, when we talk about a pair of points, it's always one point times a number equals to another point. So the G will just serve as this first point. We have to start from one point. G is that point. And then we compute G times all these different numbers. So now we are going from the number, the space of the number into the space of elliptic curve points using G. And the left side is private because we can, the T is private, all these numbers private. We can guess T from these values. And the right side is all public. Right side is encrypted. They are hashed. You cannot figure out the left side from the right side. So that's the setup from the trusted party, third party. The trusted third party also picks a few other secret numbers. They're also secret. And we compute these other numbers. We multiply okay, sorry. I think there is a typo here. This should be B. So we further times this point with Ka, Kb, Kc, and then we also add them together and times it with Kk. In a few steps, you will see that this point and this point, and you can you see like a G. Look at this one, G times A1 and G times A1 times Ka. This is a pair of points that differs by Ka, right? And later we will plug that into this KOE property to use them like this. Like a Q1 is equal to P1 times K. And here, G times A1 T times Ka is that number times Ka. So the K is the secret difference here. And later we will show you that some, use many points. We can show that this linear combination knowledge of exponent. So this is what we gradually reach a point, we can apply the previous knowledge of exponent property. So what I just showed you is the trusted third party pick out this secret, and G is not a secret. And the transformation, the preprocessor not only get all this QAP representation, but also will lift them to the elliptic curve space using G. And for the AI, it will compute both G times AI and also G times AI times Ka. The same thing for B and C. And for this thing looks a little weird. We'll explain that in a moment what that is. And you can see none of this is in the proving yet. It's not a part of the proving process. It's all a pre-processing. The prover, however, will use this to generate the proof. You can also see that none of this, it depends on actual execution. The execution, each execution will give you a state vector, witness vector, and none of this depends on that. So this is you only need to do this once for each program. You do not need to do this every time you execute a program. So now let's go to the first part of verification. So let's look at let's look at A first. Only look at A. The left side is private. They are the previous QAP representation of the program evaluated at this secret point T. On the right side, there are two pairs of points, not two pairs of points, many pair of points that are derived from these numbers. So those are already evaluated at T. So these are actual numbers. They are not polynomials. So these are not polynomials. They are numbers. And here are elliptic curve points. The n here is the number of steps in the program. Wait, no, I don't think. So this is not the number of steps. I think n here is the. Let me go back to see. I think n is the number of states. Yeah, n is the number of states, not the number of steps. Because previously we used n to represent the number of steps here, steps in the program, but here the n is actually the number of states. So we zoom into A, and using the witness vector, the state vector of the execution, we can linearly combine. So previously we linearly combine this different QAP polynomials to get a single polynomial, right? And here we can do exactly the same thing to linearly combine these two pair of points. Because like G times A1T is just A1T transforming into elliptic curve space. So by previously we are linearly combining these polynomials, and now we are linearly combining these points. It's exactly the same thing. It's just we're doing it in the elliptic on the elliptic curve. Remember, the elliptic curve also have a scalar multiplication and addition defined, so we can perform the same weighted sum on all these three things: the polynomials and also the elliptic curve points. Yeah, so this is more like a recap of previously what happened. AX evaluation point T is a linear combination of all these different polynomials evaluation at T. And we can do, yeah, like so we can do the same thing for this two lists of points. So we end up with the polynomial A. So this polynomial A is exactly the same as the previous QAP polynomial A here, because underneath is just a linear combination. So by linearly combining these points using the same weights, the state vector, we can get G times AT, the polynomial evaluated at the secret point T, and the G times AT times Ki. So you can see the evaluation here compared to the previous evaluation, one of the big difference is that here the prover does not know what T is, but the prover can use these pairs of points to compute G times AT and also be able to compute G times A evaluate T times Ka. So that's a very important thing, that the prover does not know what T is, but the prover can evaluate its own polynomial at this point. Given the public available, yeah, I think this is basically again talk about the same thing. We given these points public, and the execution, which is state vector. We can summarize the execution into these two elliptic points. So these are two single points. It's not a lot of data. It's just 2 points. And then we can use these 2 points to verify the integrity of the execution. This is called a KZG polynomial commitment. You can read more about it later on. I think I already talked about it earlier that polynomial commitment means that it's something you can, it's like a hash for the polynomial. You can use the hash of polynomial to quickly test and evaluate the property of this polynomial at a certain point in a way that is both fast because you only have 2 points to work with, and also privacy preserving, because from these 2 points, you cannot figure out what S is, what the state vector is. Yeah, prover needs to, so prover will generate this point, these 2 points, right? The prover needs to create these 2 points and send them to the verifier, and the prover needs to convince everyone that the prover indeed compute these 2 points using this formula. And the verifier doesn't trust this. The verifier says, you just give me 2 points. How can I trust that you actually, this is from actual execution of your program? Maybe you just give me 2 random points. I want to make sure you, the prover, actually compute these 2 points from this equation. They are actual linear combination of this publicly available point pairs. Yeah, again, this is summarizing it again. So the prover give 2 points, but this slide just introduces this new notation called pi a and pi a prime. Pi a is the first point. The pi a prime is summarized with a ki multiply here. And the verifier needs to verify that whether these 2 points are actual linear combinations of this earlier encoded polynomials on the elliptic curve that corresponds to the execution of the program. So the prover and the verifier, they have a conflict of interest. One wants to prove, and the other one to validate. The other one, the verifier by nature does not trust prover, because the verifier trusts prover. no need to prove anything. Yeah, I'm just trying to summarize the same concept using many different forms. This is a graph form on the map. The prover send a bunch of this thing to the verifier, and the prover wants to say that, hey, I do have this execution vector S, and S is the vector weighting vector I use to compute these 2 points. But I cannot tell you what S is, because I want to keep S secret, but also probably because S is huge, a billion entries. I don't want to overwhelm you with so many data. So here is only 2 points. And the verifier just say, hey, how can I tell if the prover is telling the truth? Then, of course, we can use pairing to check that. And we can see, I think previously we already talked about exactly the same thing. You can check if these 2 points differ by the same points. I mean, from the verified point of view, let's go back to look at this. So the trusted third-party trusted setup, it will also give you G times A. It will also produce this one and make it public. And from this point, nobody can figure out what Ka is. But by putting this point and the G is also public. By putting them together, we can use pairing to check if pi A and pi A prime, if they are differ by Ka, right? Like this point, G and G times Ka, they are public. And using pairing, we can check if pi A and pi A prime also differs by Ka using pairing. And according to knowledge of exponent assumption, if pi A prime is equal to pi A times Ka, then pi A must be a linear combination of all these QAP polynomials points. Therefore, A is an actual linear combination using some weights instead of some randomly generated points. Let's see. That prover cannot. Yeah, Ka is a secret, so the prover cannot get information from anywhere else. The prover must generate pi A and pi A prime from all this number, all these points. So this basically proves that pi A and pi A prime are actually linear combination of these points at the bottom. So that's what we proved so far. That's what the verifier can prove so far. And this is not enough for the whole ZKP yet, but this is an important step. And we can do exactly the same thing for B and C. For B, we also do the linear combination. C do the linear combination. We'll be sure, and we can prove that pi A, pi B, pi C, they are all linear combinations of this program we published. And the next thing, we also need to make sure that this pi A, pi B, pi C, because so far we only proved that pi A, pi B, pi C, they are linear combinations of these points, but we have not proved that they are linear combinations using the exactly same weights. If you're executing the program, you must have a single weighting vector, and you use this single vector to combine both A and B and C. You cannot just say, oh, I'm combining B using different weights, A using different weights. I think earlier you can see that this is using the same S. If you derive from beginning, this 3 vector needs to be the same. So that's where like this point at the bottom comes into place. Because if you look at it, you can use this point at the bottom to verify that. So the provider provides, well, while linearly combining these bottom points, also using the state vector, using S, and you can compute this directly, and you can see that we again have 2 points that differs by KK. The first one you can combine, you can compute using pi A and pi B, pi C. The second one you need to linearly combine using this point provided, like here. This bottom line here, you can use this point to do the combination. basically, again, we just do the exactly same thing, but now we are doing like a concerning ABC. We're trying to connect ABC together to prove that they are combined using the same weights. Again, pairing, we can use this pairing check to pi k. Let me see if this is correct. Feel like wait. Oh, yeah, okay. I think this is correct. Although this one is a little confusing. I think I write it a little confusing this way. This pi k should really be this. Yeah, okay. So pi k is computed this way, but it should equal to this. It should equal to this. And if you plug in here, you can use pairing to check that if pi k is indeed k like indeed like this two thing indeed differs by a multiplier of kk. And if so, these points must be a linear combination of that. Therefore, these three weights must be the same. Because if S A, S B, S C are not the same, then pi A, pi B, pi C cannot be a linear combination of this list of points. Okay. So what we have verified so far? We have so far verified that pi A, pi B, pi C, they are all linear combinations of the program's QAP points, meaning that they are all, and also they are combining using the same weights. But there's still one thing missing. There's still one thing we have not proved yet, which is that we have not proved this thing exists. We have not proved that they are zero at this point. We have proved that AX, BX, CX, they are linear combination of the program, but we have not proved that they equal to ZX times HX. So so now just imagine that we have ZX and HX evaluated at point T, and also we have them transformed into the elliptic curve. Remember that pi A, pi B, pi C, they are essentially come from ABC. Sorry, I just need to go back a little bit more. Because there's a lot of a concept here. I want to make sure it's clear. Yeah. I think somewhere. Yeah. So pi n and pi. Basically, pi n, pi b, pi c is the polynomial. The ABC evaluated at the secret point k, at secret point t, and then transform into the elliptic curve space. And we can do exactly the same thing for the z polynomial and h polynomial. These two polynomials, we can also evaluate them at the secret point t, and then multiply them by g, by the generator, to transform them into onto the elliptic curve. Suppose we can do that, and then we can use the following equation to verify. So then we can use this following equation using three different pairings to verify this equation on the top, and we will show you why that happens. So in other words, you can compute the pairing down here using all these points, because all these points, the G is public and all these other pi's provide a prover. So you have the verifier have all the information it needs. The verifier, now I'm just claiming that the verifier can compute this equation to see if this equation is true. If this equation is true, then it just means that this equation on the top right is true at the point T. So I'll show you why that's the case. And if this top right equation is true at point t, according to the lemma, this is true everywhere, and then the program, then the proof basically is done. First of all, there is this simple derivation that if left side is p minus q is equal to this, is a division, and you can easily rearrange this to see that this is true. Just like move things around. I will not go to the detail, but you can look. It's not complicated. Then you can get this equation, and you start from this equation at the top, right? This is just like from the lemma. This equation evaluates t is true at t. Then you can expand that into linear combination of this QAP, like sub polynomials. And now we are what we are doing is to we are just like a compute pairing between this one and the g. So I think earlier we talked. So if you look closely, we didn't do much here. We just moved this whole thing onto the left side of the pairing. Not the first argument of pairing, and then the second argument is g. Here is the same thing. We move this here and the g. So if this two number is the same, then the bottom will definitely be true. Right? If you not follow, you can later look at this, because I think I made sure each of this step is super simple. So there's no like a jumping ahead, a big jump. Then you can rearrange this. Let me see what's the rearrangement here. Okay, so this line, the first line is identical to the last line here, so there's no change here. But now you can, you just like move g, attribute g to both of these terms. Here's the left multiplication, and you times g to here, and this one is basically pi c, right? This is pi c. So furthermore, you can move this ht out, and then move this ht in to the other g. You end up with pi z and pi h on the right side. So finally, to this term, like earlier we talked about minus, you will become division outside. So you can move this thing out and move to the right side to reach this. And finally, let's see what's happened here. You can move this s times bit out, and then move it into the other side, move to the other g, and you will see this are pi and pi b. So it's like a derivation. It's not obvious just by looking at this equation, but if you follow step by step, it works out pretty easily. So we talk about that if you have pi z and pi h, like this two equations evaluated at t, transform the elliptic curve, and then you can do all of this to finish the proof. So now let's go back to talk about how do you get pi z and pi h. Pi z is relatively easy because z is almost like a constant. It doesn't change much. It's just like a t minus 1, t minus 2. If you know n, then you can easily come with n is the number of steps here. Then you can easily come with zt. It's identical for different execution of the same program. It's also identical for different program with the same number of steps. And I think this one you can. It's part of a pre-processing. I made that public. That's fine. Still want to see. If you look at the map, you should be able to see that. Sorry. Yeah, the pi z is here. It's just like it's just a public thing. Pretty easy. The edge is slightly more complicated. For each execution, the edge will be different. You need to factor the polynomial for each different execution. And because edge is changes from execution to execution, how does the prover come up with it? It turns out this method that the trusted third party will compute all this g times t squared, g times t cubed until like a g times t raised to the power of a very large number, such that no matter what h is, if h is a high degree polynomial, you can still use all these components, these pieces from the trusted third party to assemble pi h, which is g times to the h t. So this graph shows that the prover will use this thing from trusted third party to assemble pi h, and pi z will be just computed by the preprocessor. And also the pi a, pi b, pi c is here, pi k is also computed by the prover. So here you can see the pi a has I put a little tilde next to it. Let's ignore that. I will explain what that is in a moment. So I'll stop here for a few seconds to see if there's any questions so far. Any questions? Okay. And so far you can see that also on the right side here shows all the verification the verifier needs to do. It involves a lot of pairings. Also, once the verifier does all of this pairing check, it's identical to the earlier check that basically you can now see the a times b minus c equal to z times h is true everywhere. So essentially, you proved what we want to prove earlier. The program indeed gives this output, gives the input. But of course, there's still one thing that we have not addressed yet, which is we have not factored in the public output and public input yet. Also, so next we will talk about how do you plug in public output and input into this proof? Because so far the proof, everything is a secret. Suppose there's a function, you give it 3 and it output 5. Now I need to prove that this function indeed gives 5 when input is 3. But so far in the proof, we have not factored the 3 and 5 into it. We just it's just like a single proof. Say, I have some execution of this program. But indeed, we want to prove that not only you have an execution of this program, but this execution has 3 as the input and 5 as the output. That's what we really want to prove. But before I explain that, let's just take a moment to see that right now, the verifier, given pi a and pi b, all of these pi's, it actually cannot know the witness vector. It does not know the state vector. It does not know exactly how the program is executed. In other words, the privacy is preserved in this mechanism. It's not only quick, it's not only fast, but also does not leak information from the prover. So we essentially have achieved the two things we want to solve earlier: make it fast, make it preserve confidentiality, and now we just have a last step to plug in the input and output. Yeah. Actually, yes. I think there's like a fast Fourier transform to compute that. I'm not too familiar with it, but I think there's like a fast Fourier transform you can prove that, and not prove that. So this is a great question. The question is how if you look at this, and I think maybe I can zoom in. Yeah, here's you need to compute h as like a times b minus c divided by z, and h is called a quotient polynomial. And if you compute it naively, it's pretty slow. If it's this polynomial is a billion terms, it's pretty slow. And in some cases, you can compute this quickly using fast Fourier transform. Wait, can I say it again? What do you mean by coefficient way? G times the. Oh, okay, yeah. Oh, no, no, no. So are you talking about this evaluation? Like, wait, so the polynomial. Wait, let me see this. Okay, so there are several ways to do that. I think one way to do that is you lift all these terms into you transform into elliptic curve point first, right? That's the first thing you do, and after doing that, t is a secret, however, and now you use all of this to assemble this different number like points, right? This now you are like use those general points in the elliptic curve to come up with this point corresponding to the QAP representation of this specific program. And so far, there's no edge yet, right? And now, given actual execution of the edge, execution of the program, now you can compute edge, right? And after you this, so edge here is still just algebraic, like a polynomial, and then you can use all of this to assemble the G times edge. Sorry, yeah, can you ask again? Maybe I didn't answer your question. Understand your question. This one? Okay, so your question is like, is there any fast way to compute the quotient polynomial? So so let's first get on the same page. And this problem have nothing to do with elliptic curve, right? This, yeah, it's just like an algebraic problem, right? Just like give two polynomial, how do you divide them? Yes. So I don't know too well how that, but I know fast Fourier transform is the common way to accelerate that in zero knowledge proof. Yeah, I think you can also do that on like a GPU, and maybe it has some restrict. Yeah, I think you have to like look online on that. Yeah, yeah. I think fast Fourier transform should be the way to do the division. Okay. Yeah, great question. Yeah, we will talk about the proof. We need to prove involving query and output, not just the proof. So the solution is actually very easy. It's very straightforward. Previously, we are saying let the prover assemble everything, right? But because of the like here, the in and out, these are public input and public output. We can simply solve this problem by let the verifier assemble these two lines, and let the prover assemble the rest of the lines. Basically, the prover does not sum up all the equation like a polynomials. It only sum up accumulate everything that is does not have public input and public output, and then the rest will let the verifier to add them, because you remember all these points like a G times A1, those are all public. So prover can do that, but public can, like a verifier can also do that. Verifier can do that because these two weights 3 and 35, they're public because they're public input and public output. Verifier knows that. Yeah, the prover assemble AI for the private inputs, and so the tilde, I'm just saying that by putting a tilde here, I just use that to represent that we're ignoring entries in S that are public. And then the verifier will assemble the rest using public inputs and public output, like I showed here, but only counting public values in S. We do not do that for B and C because A is enough. Earlier we already proved that A and B and C are combined using the same weights. So if we prove that the public inputs and the public output matches the weights in A, we do not need to do that again for B and C. So we only need to do that for A. Okay, cool. So we do, I think, finish the whole proof. Now let's recap a little bit. So this is just a recap for the last part. The trusted third party created the secrets, the generator G, and also compute all these different points, like a raising T to the different power. This is the first line, raising T to a different power. And it also compute like a raise T, like a multiply Ki, Kb. So this, the first line is for the prover to assemble the pi edge. And these three lines, these four lines is for the preprocessor to assemble G times AI times Ka, G times Bi times Kb, etc. And the last line is later when you check the pairing, you will need this like G times Ka, Kb, Kc. I think I got this right. So you need to compute a bunch of things, all of them encrypted by using elliptic curve. And then the preprocessor will take this information and also the QAP representation of the program and combine them into all these point pairs. And all of these things will be sent to the prover. And the prover, getting the witness vector from the execution. I mean, here I'm like dividing executor and prover into two different parties, but in reality, they might be the same. Like I might be both executing and approving I'm right, but I can also be executing the program and let someone else prove it for me. So this is still conceptually two distinct steps. You execute the program first, and then you use all of this to prove the execution is correct. When you generate the proof, you use all these things to come up with pi b this, and ignoring the public input, public output. Then the prover, the verifier will get the proof from let me see. The verifier will get the proof get all this pi for sure, and also get public input, public output. Let me see why I put this arrow here. Because the verifier does not really need so the verifier, I think let me see. So the verifier does not need this data directly, but this data are essentially public. So the verifier, if they want, I think they can verify. I see. Okay. One second. Let me see. Why do I put that arrow here? Okay. Oh, okay. So I remember why. So because the verifier also needs to assemble part of the proof, like need to assemble these public entries corresponding to public input and public output. So it will still require some of the G times AI and G times AI times Ka. So because it needs those points in order to assemble this final pi and pi prime. That's why I put this arrow here. And after you assemble all of these values, the verifier can quickly verify that the execution is correct. And this proof is very slow, very small. I think it's probably 288 bytes with probably like around 100 like bit security, and that is for any size of the program. The program have like 1 billion, 10 billion step. All of them can be proved using only 288 bytes. and the checking is also const time, just a few pairing checks. Yeah, there's a complexity. The complexity, because the verification, you also need to assemble part of the proof. So the verification is essentially, the time is basically proportional to the public input and output length. The actual checking is constant time, but the input and output length, it can be variable. It can be, you can have many, it can be have a large input and large output. Of course, if you want to really push, use zero knowledge proof effectively, you do not want the public input output to be too large. You want them to be small. And yeah, if you are using like zero knowledge proof to prove, for example, okay, let's like do this review first. So I think this this is a summary of the zero knowledge proof algorithm, and I have highlighted those places that there are some fundamental change, not just like a form transforming from one form to the other form. Like I said earlier, that Lagrange interpolation expand the problem from like a discrete points into the continuous space access, and the single point test lemma let us use one point to test the identity test between two polynomials over. So you just shrink the problem from the whole axis into one single point. And on the bottom right, we have pairing check plus knowledge of exponent. That's the KZG commitment. Let us evaluate the polynomial at a secret point very efficiently. And then finally here, the verifier will collaboratively assemble the proof. I think this last one I put here is because there's a trust gap here. Basically, I want to highlight that it's the prover and the verifier collaboratively together assemble the proof. The verifier needs to assemble the public part by itself to be sure that this proof indeed corresponding to this public input and output we're talking about. And I do think that is a pretty fundamental thing here. It's not only a transformation of forms. There's a trust. There's a conflict of trust there. Okay, so we have already finished the math part. The rest we'll just talk about some practical issues and some like industry trend. It should be relatively quick. And so these numbers, they are secret, which also means that anyone with these numbers, they can fake proofs. They can create pi a prime equals to pi a times ka without linearly combining this QAP polynomial points. Therefore, this number needs to be really kept a secret. But how can we trust this? Because if you think about it, if you let this trust the third party, then did we go back to the Web2 world that we centralized? We're trusting a single party. It turns out there's a pretty neat way to create this secret that is still relatively decentralized. It's called a MPC ceremony. What it does, so conceptually what it does is to say, let's get a lot of people who don't know each other together, and everyone will contribute some randomness into this protocol called this ceremony. And this randomness will mix together to create this secrets. And the cool thing about this is that nobody knows what this secret is. Everyone contributes randomness to it, but nobody knows what the secret is. If everyone participated, come together, say here, hey, my secret is this, your secret is that, everyone put their secret together, they can figure out what these numbers are. But if only one person refused to join this, if one person say, I don't want to share my secret, I want to discard my secret honestly, then people cannot figure out what T is, what Ki is. We will get that. So this is really cool because if you do not trust these people, if they say, hey, I think you guys are colluding, you are trying to find out secret, you can join them. You can join them, contribute your own randomness. Then you discard it. Then you can trust that the secret is indeed secret because you participated and you discard your secret, discard your randomness. So this ceremony has been done several times, and there are some ready-to-use one that you can download online. And I think they are pretty secure. This only need to be done once, and then it can be used to pre-process many different programs as long as the program does not exceed the degree. Because here we can't like compute raise t to the infinite degree. We can maybe raise it to 2 million degree or something. Then that's a trusted setup. As long as the program fit into that degree, you can reuse this trusted setup many times. Yeah, you can read more about this setup here, and you can also download the previous setup from this website. So that's the trusted setup. For lab, I don't think we can get into too much there. I was previously planning to have this lab in the class, but I'll just explain it here. If you want, you can go to look at it by yourself. I don't want to say that right now because zero knowledge proof is still not that mature. So most of the tools are not that easy to use. But this is one of the tools I find is pretty straightforward to use. It's called Snark.js. Yeah. If you go to this thing, you will have like a kind of 20+ step tell you how to create a program and how to run the program, how to generate proof for a program, how to verify the proof on chain, how to verify the proof locally. So it gives you this end-to-end pipeline for developing zero knowledge proof programs that you can use in your blockchain project. This is executing off-chain and verify on-chain is a very typical pattern for zero knowledge proof for a few reasons. One is the blockchain's computation power is very limited. So many people, they like to do intensive computation off-chain and then prove the result on-chain. So the trust is as good as if everything was done on-chain. But the computational power is a lot more available off-chain. So that's one reason that people like to execute off-chain and verify on-chain. So if you're interested, I'm also personally doing a startup in exactly this area. We want to execute the games off-chain and verify on-chain to dramatically speed up the game execution speed. We want to basically have the Web2 speed with the Web3 trust. If we have time, we can talk about that more later. The other reason people like to execute off-chain and verify on-chain is that everything on-chain is public, is transparent. There's no privacy. But if you execute things off-chain, you can keep a lot of things private and then verify on-chain. For example, I want to prove that I have something that hashed to this value, then you can prove that, then we can generate that proof off-chain using zero knowledge proof and then verify it on-chain, something like that. So execute off-chain and verify on-chain. This another benefit is you can be private. Yeah, like I said, if the lab is you write a program that compared to zero knowledge circuit, R1CS is one such circuit representation. Run the program with certain input and generate the proof, then verify the proof possibly on chain. Now there are many languages you can use to write programs that compile to circuit. One of them is circum. There's some document and the tutorial here. Maybe I'll put. So if you want to work with circum, I think one thing that I want to talk about that will, I think, make it easier to ramp up is to understand that, because so on the right side is a circum program. One thing that can be pretty confusing if you work with this language for the first time is that you need to understand that this program, there are two programs put together. One of them is execution, the other one is verification. So in other words, here you see there's an executor and a prover, and circum essentially in some sense combines together into one program, so that when you write program here, some of the lines are like, for example, this line is executed and also verified, and this line is only executed, it's not verified. In other words, like the var I equals small line, this is not verified. And some other lines, this line on the bottom left, it looks like an assert in like a or like other programming language. It does not execute anything. It just checks that this thing holds. So the execution is just the execution, and all this verification, they will eventually be transformed into this QAP representation, and you know, be transformed into QAP and the elliptic curve points, all of those for generate the proof. So this program has both execution that generate the witness and verification that generate the proof. So they are in the same program. There's some ideas what you can do. Maybe you can calculate the Fibonacci number, or you can create some games and the Merkle tree inclusion. There's a lot of things, cool things you can do with zero knowledge proof. I encourage you to try different ideas, and the hard hat circum plugin can be pretty handy if you for you to organize and automate some of tasks. So let's very briefly talk about what's happening today. So the math we cover in this class, it was invented in 2016, 8 years ago. And circum probably already have like maybe 5 years history at least. I can't remember clearly, but there has been a tremendous amount of things happening recently. So I'll cover them really quickly here. So the first thing is that there are many forms of polynomial commitment. What we have go through, the commitment is basically everything except the polynomial transformation and the lemma. Is like the elliptic curve, all of that. It's called KZG commitment. I think it's the first letter of 3 persons' last name. Yeah. And there is also other form of commitment like FRI, IPA, etc. And they all have different property. There's a few things worth notice. That is, I think let's look at this bottom left table. Transparent just means this zero knowledge proof does not require a trusted setup, which is a huge advantage. KZG do need a trusted setup, but some other proof does not require trusted setup. Post-quantum also means that it's secure even if we have quantum computer. This is because some of the assumption in the elliptic curve, for example, you cannot guess k, does not hold anymore if you have quantum computer. But so some of this other polynomial commitment does not rely on any of this assumption that can be invalidated after quantum computer. The bottom right table is also useful. You can see that KZG is extremely small. It's extremely fast. That is partly why it's still very popular today. Some other proof technique, you can see they might be transparent or post-quantum safe, but they are They have larger proof size and verification time. We talk about there are many different languages that you can compile into circuits. For example, Circum, etc. And one of the big trends